Welcome to 3.7, optimization problems. Optimization, what does that mean? Finding the best thing that fits the situation. So, students often ask me, this is a very true thing, I talked about this when we started this chapter, when are we going to use this? Which is kind of an insulting question. Aside from the intrinsic value of knowledge and the extrinsic value of preparation for one's chosen vocation, a lot of people engineering, science, even math. One very useful application of calculus is finding the minimum and maximum values of functions through taking derivatives. If you can model a situation with an equation, you can find the maximum or minimum value of the function. I crossed this out because I had the function twice. By taking the first and second derivative. In pre-calculus, you might remember we did this when we had parabolas. We could find the vertex of the parabola, but we don't just deal with parabolas. We deal with lots of different functions. So now we have other tools to do that. So guidelines for solving applied minimum and maximum problems. 1. Identify all the given quantities and all quantities to be determined. If possible, make a sketch. Write a primary equation for the quantity that is to be maximized or minimized. A review of several useful formulas for geometry is presented inside the book. Reduce the primary equation to one having a single independent variable. So you might have two variables, you've got to work it down to one variable. This may involve the use of secondary equations related to independent variables of the primary equation. Determine the feasible domain of the primary equation, that is, determine the values for which the stated problem makes sense. If you're talking about people, negative people wouldn't make sense. Another negative people. You can have a negative quantity of people though. Determine the desired maximum or minimum values by the calculus techniques discussed in sections 3.1 through 3.4. So, example 1. Now, you've probably seen this one in your pre-calculus days. From the length and width of the rectangle that has an area of 64 square feet and a minimum perimeter. So in this, length times width is 64. And so we have a relationship for length and width. Now perimeter is 2 times L plus 2 times W. If we solve for L, L is 64 over W. We could take that 64 over W and put it in place of this L and have an equation P equals 2W from here plus 2 times 64 is 128 over W. So now we have perimeter as a function of just the width. And then we can take the derivative. So notice that this goes in place of length, which is down there. So our perimeter is 2 times the width plus 128 times the width to the negative 1. So if I take the derivative of the perimeter with respect to the width, I have the derivative with, well, what's this derivative going to be? 2 plus negative 1 times 128 W to the negative 2. So our P prime would be 2 minus 128 over W squared. So if we take that, set it equal to 0, 2 minus 128 over W squared equals 0. That means 2 equals 128 over W squared. Multiply both sides by W squared. 2W squared equals 128. Divided by 2. W squared is 64. So the width would be plus or minus 8. What makes sense is positive 8. The width would be 8 meters. Feet. 8 feet. So the length would be 64 divided by 8, which is also 8 feet. And that's a square. And that makes sense that a square is going to have the most efficient use of area for this shape, for a rectangle. 8 by 8. So our perimeter is going to be 2 times 8 plus 2 times 8, which is 16 plus 16, which is 32 feet. That's the minimum perimeter for an area of 64 square feet if we're talking about a rectangle. And to be fair, a circle would be the most efficient use of space, but we're talking about rectangles here. Okay, let's go on to page 2, or page 3, example 2. I gave a lot of space for each example here. Now, this one says find the point on the graph of the function that is closest to the given point. So we're talking about f of x equals square root of x is the function, and the point is 4, 0. So here's 4, 0. So this closest point is going to be located at x comma square root of x, xy, or x square root of x, because this function is going to be f of x equals the square root of x. So if we use the distance formula, that's going to be the square root of x minus 4 squared plus the y minus the y value, so it's square root of x minus 0 squared. It's going to be x squared minus 8x plus 16 plus x. So d equals the square root of x squared minus 7x plus 16. Now, consider the stuff under the radical. F of x equals x squared minus 7x plus 16. And I would argue that the maximum value, or sorry, the minimum value here would be the minimum value in there. It's a reasonable assumption to make because we're talking about a radical. So f prime of x would be 2x minus 7. So if we take 2x minus 7 equals 0, 2x equals 7, or x equals 7 halves, which is 3.5. Also, f double prime of x is just going to be 2, which is positive. Now, this graph is not the graph of this function we're defining. This graph is the graph of the square root of x. So while the graph is concave down, what we're saying is the second derivative means it's concave up, which means the critical value we get is always going to be, it's going to be a minimum. So concave up, which means 3.5 comma f of 3.5 is a minimum. So x comma square root of x is going to be 3.5 comma the square root of 3.5, and that's going to be our point. I should say f of x. Okay. So we got to use our tools here. We got to define a new function, and then realize that, I mean, we could take this derivative, but that's going to be a lot more work than just looking at the stuff under the radical. And we can make that leap. I don't think it's a big leap, because the minimum here is going to be the minimum there. Okay. Feel free to pause that one. Let's go on to example 3. This is a very popular problem. I think I always get this on the test, so I hope I remember to put it on the test this year, on our midterm. A farmer plans to fence a rectangular pasture adjacent to a river, so you have 3 sides to fence, and then I guess the cows are smart enough not to go in the water and get washed downstream. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Now, you could do this without calculus if you wanted to, but we have calculus, so we'll use that. Our area is going to be x times y, and that's 180,000. So y would be a 180,000 divided by x. Now s is the length of the fence, and s is going to be x plus 2y. So we want s to be equal to x plus 2 times y. Y is 180,000 over x. So s would be equal to x plus 360,000 over x. And our first derivative, s prime, is going to be equal to 1 minus 360,000 times x squared, because you could represent this as s equals x plus 360,000 x to the negative 1. This negative 1 comes out front, and this should be negative 2 power actually. So if we set 1 minus 360,000 over x squared equal to 0, we have 1 equals 360,000 over x squared. So x squared equals 360,000. So x would be equal to plus or minus the square root of 360,000. So x, we'll just go with the positive because the negative doesn't make sense, 600 meters. Now, if we do the second derivative, we will end up with what? That's 0. We're going to have negative 2 times negative 360,000 x to the negative 3, which will give us 720,000 over x cubed. If we look at the second derivative at 600, that's going to be 720,000 over 600 cubed, and that's going to be positive. So s of 600 is a minimum value, because that means the function's concave up at that point. So for x being 600, y would be 180,000 over 600, which is, I believe, 300. So x equals 600 meters, y equals 300 meters. Okay, let's go on to the next one, so feel free to pause that. Okay, the next one's going to take a little more space. We have a lot of formulas to work through. Okay, for the next one. Surface area. Solid is formed by joining two hemispheres. So a hemisphere is half a sphere to the ends of a right circular cylinder. The total volume of the solid is 12 cubic centimeters. Find the radius of the cylinder that provides the minimum surface area. Okay, so we have the minimum we're after. What we have is half a circle, so we have one circle plus one cylinder. Now for surface area, we don't have to worry about this part of the cylinder or that part of the cylinder. So our volume is 12. So this says 12. That's going to be 4/3 pi r cubed. This is the volume of a, not circle, it's a sphere, I'm sorry. Okay, that's the volume of a sphere plus the volume of a cylinder. Okay, so we have 12 equals this. H is fixed. R is the thing that's not fixed. We want to solve for H, so we can put H when we look at the surface area. We could have it all in terms of one variable. Okay, so if I subtract 4/3 pi r cubed, I have 12 minus 4/3 pi r cubed equals pi r squared h. And divide by pi r squared. H would be 12 over pi r squared minus 4/3 r. Now, for the surface area, of our sphere, surface area is going to be 4 pi r squared. And now for our cylinder, though, if we unroll that cylinder, what we're really seeing is just a rectangle, where the height of that rectangle is h, that's this h, and then that length across, that length is the circumference of this circle, so that's pi r squared. So for this, the area is going to be pi r squared h. I'm sorry, that's 2 pi r. So it's 2 pi r h. So our total surface area, S, is going to be 4 pi r squared plus 2 pi r h. So the issue is that we have an h in here. We're going to put this h in place of that. So this value for h in place of this h. So S equals 4 pi r squared plus 2 pi r times 12 over pi r squared minus 4/3 r. So S, come over here, S equals 4 pi r squared plus, if you 2 pi r times 12, it's 24 pi r over pi r squared minus 2 pi r times 4/3 r, that's going to be 8 pi r squared over 3. Now, we can combine this term here and this term. So think of this as 12 pi r squared, 12/3 pi r squared minus 8/3 pi r squared. So S would be 4/3 pi r squared plus 24. Over here, the pi's divide out the r's and that r down there. So it's 24 over r. So you can think of that as 4/3 pi r squared plus 24 r to the negative 1. So S prime of r is going to be 4/3 pi times 2r minus 1 times 24r to the negative 2. So we want to put this first derivative, set it equal to 0. So call it 8/3 pi r minus 24 over r squared equals 0. To get the critical numbers, that means 8/3 pi r equals 24 over r squared. Just moving that over. Multiplying both sides by r squared, we'd have 8/3 pi r cubed equals 24. So that r cubed equals 24 over 8/3 pi. And r would be the cube root of 24 over, well, 24 divided by 8 is going to be 3. That's just going to be 9 over pi, right? And we're looking at there. Let's leave it like that. 9 pi, the cube root of 9 over pi. Now, here's what's interesting. If I take this value and put it back into h as a function of r, so h of the cube root of 9 over pi is 12 over pi times the cube root of 9 over pi squared minus 4/3 times the cube root of 9 over pi. This works out to be 0. So what we're talking about is the minimum surface area means that you have a height here of 0. And that kind of makes sense because the most efficient use of that space is going to be a sphere. So the most efficient use of this cylinder with hemispheres is not a cylinder at all, it's just a sphere. So the minimum surface area is a sphere. Kind of cool. Okay, we have another problem to do. And I'll go ahead and move on, so feel free to pause that. So this last one from this section. Now this problem is popular in many circles, including one where the same type of problem could be set up for a dog. And there's a guy who wrote an article called "Does My Dog Know Calculus?" And the idea here is that dogs have two speeds, a running speed and a swimming speed. The guy was on shore, like at the oil refinery, threw the ball out here to the offshore well type area. Not the same thing. I'm not really saying there's an oil refinery here, but I'm saying here's the guy, throws the ball here. The dog could just swim directly out there. The dog could run out here and then swim, or the dog could run so far and then swim. And that's what the dog does. The dog had chosen, he tested this, the dog chose the most efficient path. How does the dog know that? I mean, how do these animals know what the most efficient path is? Well, it's because the dog has this innate understanding of his running speed and his swimming speed and can get there. Well, not like the dog sat down and did a calculus problem. Okay, so minimum cost. So the dog was trying to get there at the minimum time. Here we have minimum cost, the cost of laying pipe. We have cost of laying pipe over the ground and over the water, or under the water. So an offshore well is 2 kilometers off the coast, so it's 2 kilometers away. The refinery is 4 kilometers down the coast. This total distance is 4. And that's why if this part is x of this triangle made, this is 4 minus x. If laying pipe in the ocean is twice as expensive as on land, what path should the pipe follow in order to minimize the cost? So this rectangle, this is 2, this is x, so this should be the square root of x squared plus 4, not 2. There's a typo there. So we want to find the minimum cost to going out so far, and then here we want to find out not find the minimum cost, we want to find the cheapest path. So we want to know what x should be. So it's 4 minus x for this, and we can get that value as well. So we have the cost is water plus land. So K is the cost on land. 2K is the cost on water. So our cost would become 2K times this path here that the pipe's going to follow. I keep thinking of the dog problem. Square root of x squared plus 4 plus k times this distance, 4 minus x. So our derivative, c prime, this is the cost function. Let's do the derivative and we'll find the min and the max. Now the maximum, you can just go out forever and then just increase this as much as possible. You could go out to here and then that way, that would be a cost, but it's going to be more money. So c prime is going to be 2k times 1/2 times x squared plus 4 to the negative 1/2 times 2x plus this derivative, which is going to be 2 times the square root of x squared plus 4 plus this derivative. I'm doing the derivative with respect to x. K is a constant. And that's going to be k times negative 1 because the derivative of 4 is 0. So c prime is going to be 2 So these 2's are going to cancel. We still have this 2 over here. So 2kx over the square root of x squared plus 4 plus 2 square root of x squared plus 4 minus k. Oh, I'm sorry. I was not thinking clearly. K is a constant, so this part's not existent. I was making this more complicated than I needed to. So that's just going to be a plus k times negative 1. So we have a minus k there. So we'll set c prime equal to 0. So 2kx over the square root of x squared plus 4 minus k is 0. So 2kx over the square root of x squared plus 4 equals k. So 2kx equals k times the square root of x squared plus 4. Now we can divide out both sides by k. The k's will go away. We want to get rid of this radical. We have 2x equals the square root of x squared plus 4. We're going to square both sides. So that 4x equals x squared plus 4. And if we subtract 4x from both sides, 0 equals x squared minus 4x plus 4. So 0 equals x minus 2 squared. So x minus 2 equals 0, x equals 2. And there's a mistake. Because when I squared this, it should have been squared here, shouldn't it? And that is a mistake. Okay, so this should be minus 4x squared. So we have, maybe I should do this instead. Subtract x squared. There we go. 3x squared equals 4. So 3x squared equals 4 means x squared equals 4/3. Means x equals the square root of 4/3, which is 2 over the square root of 3. So x would be 1.15. So that means this part's 1.15. So where do we turn to go into the water? 4 minus 1.15 is going to be 2.85 miles from the refinery. So please excuse my algebra mistakes there. Squaring both sides is 4x squared. We minus this x squared from both sides. 3x squared is 4. From there, it's a pretty easy algebra problem. That's this distance x. So 4 minus 1.15 is 2.85 from the refinery. That's how far. And this isn't miles. This is kilometers. Okay. Well, I hope this section, we hope you see the use of calculus. I know that can be a little bit of work. You've got to set things up. That's the hard part. I know word problems are a huge challenge for people because they're translating from words into an equation. And it helped when I drew the picture here. And I think this picture was in the book. I tried to recreate it as best I could. I did add some values here that you wouldn't have seen, maybe. Just sit down and work through these problems. You can do this. You can all do this. So, hope you like that. I will see you guys later. Thanks.